So this is the second of two videos on frictional forces. Relates to University Physics by Young and Freedman, Chapter 5, Section 3. So the first video had to do with kinetic friction forces and static friction forces, rolling friction forces. Now the second half, this is a long section, has to do with fluid resistance, the resistance, the friction that has to do with fluid. Interestingly enough, we have to think of two different situations with regard to this kind of friction resistance due to fluid. So first of all, there's low speeds. So if I'm jogging, believe me, that's a low speed. And so the resistance to me by air is not going to be that great, and it's going to basically follow the old formula, you know, that it's going to be proportional. The resistance of the air to my speed is going to be proportional to each other, and so basically K is some constant that we have to figure out for that resistance. If you drop a rock into water, you know, the resistance, it's going to move at a fairly low speed, and so the resistance of the fluid to the rock as it floats down is going to be roughly directly proportional. Now, what's interesting is when we get to high speeds, the formula for the resistance for the friction goes way up. We've experienced this. You know, if you stick your hand out a car window going 60 miles an hour, you know, what we call the air drag is quite significant. And so it turns out that when we get to high speeds, the resistance force isn't proportional to the speed, but it's proportional to the square of the speed. And so in that case, you know, putting your hand out a window at a plane flying at 500 miles an hour, we're going to basically have some constant D for drag. Doesn't have to be air drag, could be, I suppose, some other kind of drag, although it's hard for me to think of another circumstance. So let's go with air drag. But basically that frictional fluid resistance force is going to be proportional to the square of the speed. So that's interesting. We have to use different formulas depending on basically how fast you're moving in a particular fluid. So, interesting. Let's say we drop a rock into water and it begins to flow down, and so that's the slow speed situation. You know, where the frictional resistance force of the fluid is going to be proportional to the speed, and you know, distinguished by some constant. Well, what's going to happen is, interesting, that rock is going to reach a kind of terminal speed. It's going to reach a point of equilibrium between the friction fluid force pushing up and the weight force pushing down. Or we might put it in the meantime, as it's coming down through the liquid, mg represents the force of the weight, and then negative kV represents the frictional force of the liquid pushing back up. Vy, because we're talking a vertical up and down, you know, kind of situation. And so basically the difference between the force of the weight and the buoyancy force pushing back up, not buoyancy, but the frictional force pointing back up, is going to equal some ma, where a is the kind of the net acceleration, as it were. Now when it reaches a terminal speed of equilibrium between these two forces, then the difference between these two is going to be zero. That is to say that the force of the weight and the force of the friction are going to equalize out and be zero. And so we can use this, turn Vy into a Vt, a terminal velocity, do a little algebra and rearranging, and what we find out is that the terminal speed for, say, a rock moving through a lake as it goes down, it's going to at some point reach a equilibrium speed of mg divided by the constant k. So m is the mass, g is the gravitational constant, 9.8 meters per second squared. You know, k is whatever the constant for that particular fluid is. And now they get into some higher calculus, integral calculus, late second semester or maybe third semester integral calculus in this next section. If you want to follow the way they derive this, you're welcome to go to the book or a book, but basically they derive formulas for position, speed, and acceleration in the meantime as it's approaching that terminal velocity. So hold on to your hat. So here's the formula for the velocity at any point on its way to that terminal velocity. At any point before it hits that terminal velocity, the velocity is going to be some amount less than the terminal velocity. And so that Vy at some point is going to equal the terminal velocity times 1 minus e to the negative k over m times t. You know what k is, you know what m is, you know what t is. What is e? Well, e is fairly important constant in mathematics and apparently in nature. 2.71828, 1828 goes on to infinity. But anyway, E is very important. It's used in compound interest. It's used in different contexts. But basically, there you have a formula, and they derive it using calculus, integral calculus, for the velocity at any point before it hits terminal velocity. And so when it hits terminal velocity, e to the negative k over mt is going to basically be 0, which is going to leave vt times 1, and vt basically will be the terminal velocity. Now, we can differentiate the velocity, and if we do, we get the acceleration at any point along that way as well. And it's going to turn out to be the gravitational constant, again, times e to the negative k over m times t. Ta-da! Now, if we integrate Vy, we come up with this more complicated formula. So the y, however far down it is going to equal the terminal velocity times all of this, how long it's been going, time, minus the mass divided by k, the constant, times this quantity again, 1 minus e to the negative k over mt. Okay, not easy formulas, derivation not necessarily easy for everybody, but those are formulas that you can use, and you plug in the variables you have in order to solve for those in problems. Okay, finally, I want to talk about the terminal speed in a high-speed fluid. You know, like if you're falling off the Empire State Building, or a rock is falling off the Empire State Building. So what is the terminal velocity there, where it stops accelerating and it forms a kind of constant velocity? Well, we go back to that initial formula. The frictional force equals the drag times the speed square. Well, when it reaches that kind of terminal speed, that's going to be where the acceleration is going to be equal to mg, which is the mass times the constant of gravity. And so we do a little algebra. So we put in mg for f, we divide by d, and then we take the square root, and basically the terminal velocity of a rock falling off the Empire State Building is going to be vt, and it's going to equal the square root of mg divided by the drag. And there you have it, this second part of this chapter, or this section of the chapter, having to do with friction due to fluid. There you have it.